Maclaurin series. Now, let me show you how this Maclaurin series works. A Maclaurin series works this way. Here's what we think about. Let's just think of a function. And we'll start off with e to the x. When we talk about a Maclaurin series, or I'm going to start off talking about a Maclaurin polynomial. That means I'm not going on forever. I'm going to limit it to a specific amount of terms, maybe 4 terms. So what I want to do is, I want to think about this e to the x, and I want to find a polynomial, maybe a 4th Maclaurin polynomial. In other words, it's going to be a polynomial that has the 4th power in it, right? It's going to have x to the 4th power. So I want to find a polynomial, 4th degree polynomial, that approximates e to the x. Now, in particular, I want it to be an approximation for the function e to the x around x equals 0. Now, the fact that I'm saying it around x equals 0 makes it a Maclaurin polynomial. If I said around x equals 5, then it would be it'd be known as a Taylor polynomial. But a Maclaurin polynomial is a special case of a Taylor polynomial, and that's when we expand about 0. So as we get into this, you'll see what I'm talking about. So if you're going to construct such a polynomial, and let me just write out the general form. If it's a 4th order polynomial, it would look like this, just in general. Right? In other words, this is a really general way to write a 4th degree polynomial. So what I'm saying is, I want to find such a polynomial that's a pretty good approximation for e to the x at around 0. Okay? Now, let's think about how we would reason through this. If we're going to find such a polynomial, what we would like to happen is this. We would like for this to be the case, that p of 0 we would like to equal f of 0, right? In other words, if we're looking for an approximation, I would like for at least them to be equal at x equals 0, right? That's a reasonable assumption, right? I want my polynomial and the function to have the same value at x equals 0. Okay? That's not too much to ask. Now, not only that, I might want them to have the same steepness. I might want them to have the same derivative. So I might say, well, I want this to happen as well. Whoops, put in a 0. I want this to be the case. Okay? So I want them to be equal in value, and then I want their derivatives to be equal, and maybe I want their concavity to match as well. So we're just putting through a list of things that we think would be a good idea for this polynomial that we're using to approximate e, or this function f. It doesn't have to be e. Okay, so that being the case, you see the game I'm playing here. I might say, well, let's go ahead and make the 3rd derivative the same. And while we're at it, this is a 4th order, a 4th Maclaurin polynomial. Let's go ahead and make the 4th derivative. And let me drop the primes at this point. Okay, so we want those things to happen. And if those things happen, I think that polynomial is going to be pretty close to the function e to the x. Okay, so let's see how this would go. Let's see how we would need to do this. First of all, what we would need to do is we would need to say, okay, so let's look at this p of 0. Okay. Well, if you look at this, if you go back and look at our original up here, this thing, and if I put in a 0, everything zeroes out except this number on the end, right? See? Because everything's got an x in it. See? Everything up there has got an x in it. This, they all have x's. So when I put a 0 in, all I'm left with is this constant on the end. So what I could say is this. I could say, okay, if that's the case, let's make this just equal to f of 0. So I'm on my way to constructing my polynomial because now I have a value for a sub 0. My value for a sub 0, so here's what I've got. I've got a sub n, x n, 4. Let's do 4, not being general. Plus f of 0. There I go. Look, I'm in the process of building this polynomial. Okay, so I'm a little more specific now. Instead of a sub 0, it's going to be f of 0. Okay? Now, and this is, we're going to use it to develop this fourth Maclaurin polynomial for e, but notice I haven't even brought in e into the picture yet, right? I haven't done anything with it. Now, let's get the derivative of this. Okay, the first derivative. Well, this is going to be 4a. Okay, there's what we got. Then we got 3. So this takes us back to the early days, right? And then the derivative of that thing on the end is 0 because it's a constant, right? F of 0 is a constant. So now what do you have? You have that a1 must be equal to p prime of, well, now let's put in a 0, right? Let's put in a 0. I forgot that part. Okay. Let's see what we have. We have,
that 3a should be a 3, correct?
oh, this one right here. Did I mess up?
Yeah.
Now it's correct, right? Okay. So now if I put a 0 in here, all of these zeros go in here, what I get is a1, right? Y'all see that? Now, remember what we said was we want p prime of 0 and f prime of 0 to be equal. So, that being the case, let's make a1 to be f prime of 0. You see that? Everybody dig what we're doing? This is pretty cool stuff now. So now here's what we've got. Here I'm being redundant here. We've got, whoops, I keep doing this, right? So this is 4. And now we're at x, okay, a2, x squared. But now, look, instead of a1, we've got f prime of 0. And then we've got f of 0. Y'all see that? See how I'm building this polynomial? Now, let's take a minute and think about this. Let's check and see if what we want is happening. In other words, we want p of 0 to be equal to f of 0. We want p prime of 0 to be equal to f prime of 0. Let's see if that happens. P of 0. Well, all of these x terms go away and we got f of 0. Excellent. Now, let's do p prime. Well, if you do p prime, all of these terms right here are still going to have x in it, right? This term is going to go away, and we're just going to be left with f prime of 0. So p prime of 0 indeed does equal f prime of 0. Everybody see that? So what we found is a polynomial that matches at those two places. Now, let's do f double prime. Okay, so I'll go back up here and I'm going to differentiate this. So I get, now look at this, look what's happening here. I get 4 times 3, a4x squared, okay? And then look over here at this one, I get 3 times 2, a2x. And then the next one, I get 2a2, right? Did I do that again? Okay. Does everybody see what happened? Okay. Now, an interesting thing you want to take note of, look at this, 4 times 3. What's going to be the next derivative? 4 times 3 times 2, right? And look over here. The next one's 4 times 3 times 1. It looks like there's some factorials lurking in here somewhere, right? So we're thinking if we go far enough with this, we're going to start to see factorials popping up. But anyway, let's put a 0 in here. And if we put a 0 in here, dig what happens. All of these go out. All of these that have x's in them go out, and we just have 2a2, right? Y'all see that? Now remember, this has to equal f double prime of 0. And what I'm trying to do is I'm trying to get what a2 equals. So it using a little bit of preschool algebra, you get a2 is equal to f double prime of 0 over 2. So now we've got that one, right? Does everybody see this, how this is going? Now, let's look at our polynomial. Let's just see what happens here. Notice I wrote it correctly this time. I didn't put the n. Now, we still got a3, x3. Oh, I did. I missed. I put the n there, right? I got too haughty, right? Now, what is a2? Well, f double prime of 0 times x squared over 2. Let's call it a 2 factorial. We might as well. And then this is f prime of 0 x plus f of 0. You see? Do you see this? Now, if we continued on with this, notice that the next thing I would solve for, so I'm up here on this one, right? If I took the derivative again, look what would happen. I would have 4 times 3 times 2, a4x. And then over here I would have 3 times 2 times 1, a3. And there everything else would go to 0, right? So in other words, what we would have is this. We have, what would it be? It would be 3 times 2, a3. And remember, that's got to equal f triple prime. So look what a3 is equal to. F triple prime of 0 over 3 factorial. Now, if you want to, you can investigate this. I don't think I need to go through every term. But look, here's what we found. And if you continue this, what you're going to find is this. This polynomial is going to look a little something like this. It's going to be f of 0 plus f prime of 0 times x. See? I'm going backwards now, right? I wrote them descending powers. Now I'm ascending, right? And then what was the next one? F double prime, 0, x squared over 2 factorial. The next one, f triple prime of 0, x cubed over 3 factorial. And the grand finale, the last one, I think we've already established the pattern, is f, the fourth derivative, x to the fourth over 4 factorial. This is the Maclaurin, the fourth Maclaurin polynomial for a function, whatever the function may be, right? That's it right there. Now, so you see the pattern. We could have done a 5th degree, which we would have the 5th derivative of 0, x to the 5th over 5 factorial. Yeah. Now, if we want to talk about the series, well then, maybe we would do like this. We would say, okay, this is going to be f n, and this would be 0, x to the n over n factorial, and maybe we'll go from n equals 0 to infinity. And this would be our Maclaurin series for that function. So if we wanted to represent a function with the Maclaurin series, this is the process, this is the approach we would take. Because notice what we're doing. We're saying the function values are the same and all the derivative values are the same. And if the function value is the same for this polynomial and the function, and all the derivatives are the same, you're thinking, man, that's a pretty good, these functions are pretty close. Yeah, this is a 0 right there. Right? Because we were always plugging in 0, weren't we? Now look, this is a Maclaurin polynomial, or Maclaurin series. Yeah, that's right. Now, if we were going to do a Taylor series, let's suppose instead of expanding around 0, we want to expand around some A, right? If we were, or some C, let's use C since I used A up there. This is a Maclaurin, right? Okay. A Taylor, now a Maclaurin is a Taylor, right? It's a Taylor series, but it's just when we're expanding about 0. If we want to expand about something else, it's just a shift. In other words, we would still, everything would look the same, except this would be, well, this is the same. Okay, but we would have a c in there, and then this would be x minus c to the n over n factorial. See, everything looks the same, so this is when we're expanding about c. That's the difference. Now, we are going to primarily use Maclaurin series in our discussion of these things. But you know, if you've got the idea of the Maclaurin series, then the Taylor is just a shift, right? You shift it when, and a lot of times the Taylor is a little bit harder to work with. Okay, so now let's think about this e. So let's see in practice how this would work. We've got this lovely function, e to the x. And what I want to do is I just want to find a Maclaurin series for e to the x. So I need to get my coefficients. So look, I'm going to say f of 0. That's just e to the 0, which is 1. So here I'm building my polynomial now. I'm building this series. It's going to be 1 plus. Now, the next term, so this right here is f of 0. Now, you know the next thing I need is f prime of 0, x. Well, let's do f prime. Well, that's just e to the 0, which is 1, right? Okay, so we've got 1 times x, and that's it. So that one's simple, right? 1 times x. Let me make it a little bit. Okay, now then the next thing we want is f double prime of 0, x squared over 2 factorial. That's the next thing we want. Okay, so let's see what we've got here. I've got f double prime of 0, and the good thing about e, you know, it's just there's no problem differentiating it, right? Okay, so now here's what we've got. We've got 1 times x squared over 2 factorial. See, what we're doing is we're generating the coefficients. The coefficients of x squared is f double prime of 0 over 2 factorial. The next one would be f triple prime times x cubed over 3 factorial. What was that? That's x cubed over 3 factorial. Y'all see that? Now, this is a third Maclaurin polynomial right here. We just go up to the third derivative. But if we want to talk about a series, we would say, well, look at this. This is x to the n over n factorial. And I guess the n goes from 0 to infinity. There's your Maclaurin series for e to the x. Does everybody see that? Now look at what this looks like. This is 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and it goes on and on forever, right? That's right. It's going to. That's a good point. We haven't even talked about, does this really converge to e? We'll talk about that later. But we can see it looks like it's going to converge, right? I mean, if we analyze this, we'll say, yeah, that converges. But let's just look at this right now. since this is e, since I'm telling you this is e to the x, what do you expect to happen if we differentiate that? If I differentiate this thing, I should get itself back, right? Now, and if that doesn't happen, you're thinking, well, I don't know if that series is e or not. So let's differentiate it. Let's differentiate. So I've got this thing, right? I've got x to the n over n factorial. N goes from 0 to infinity. And let me differentiate it. Well, I've got n x to the n minus 1 over n factorial, right? Whoops, let me put, okay, so this is the derivative with respect to x. Okay, now, let's see what we get here. This, is that the same thing? What do you think? Well, let's take a look at this. Let's take a look at this part. We have n times x to the n minus 1, and down here we have n times n minus 1 factorial, right? Do you see how I can write n factorial as n times n minus 1 factorial? These cancel, right? So this doesn't look exactly like this, but you can see that really I could write it this way. I could write it as, whoops, yeah. Well, let me not mess this up. I could write it this way. I could write it as x to the n minus 1 over n minus 1 factorial. And what if I start this at 1 and go to infinity? Let's see if it generates the same terms. In other words, I should get 1 plus x squared over 2 factorial plus x cubed over 3 factorial. Let's see if it generates that. Well, if I put in a 1, I get a 1, okay, right? And then if I put in a, look at this. If I put in a 2, I just get x. What if I put in a 3? I get x squared over 2 factorial. Oh, look at this. And it goes on and on. That looks exactly like this thing right here. Right? Yeah. Yes, sir.
So how did you do the n minus 1 thing? Why are you allowed to do that?
The n minus, well, you realize you're talking about why did I adjust the index of summation here? This, in other words, this right here? Well, you realize what we do with these indices, it doesn't really matter. Because remember, what we're trying to do is accurately expand this thing. In other words, if I start this, in other words, this is just notation, right? And I could have done this. I could have just went back here and differentiated this and then rewrite that, well, because I was wanting to show that if I said this Taylor series is e to the x, we know the derivative of e to the x is e to the x. So what I wanted to do is differentiate it and show you, yeah, it is e to the x.
I forgot that we differentiated it.
Okay, I got you. Yeah, so we can adjust these indices. And oftentimes when we differentiate, we have to. Okay, now, any questions about that? Okay, now, so here is what we need to realize. The Maclaurin series expansion for e to the x is this thing. That's the Maclaurin series expansion.